So in this tutorial video, I go into some depth on fitting gpvdm to transient data as well as steady state data. In the past, I've done a video on how to fit gpvdm to a single JV curve, and that was quite a quick and easy thing to do. However, if you want to sort of narrow down the parameter set, so mobility and density of trap states and recombination rates, things like that, a bit more accurately, you have to fit the model to not just one data set like a JV curve, but maybe multiple data sets, because some parameters are very hard to get from JV curves. For example, the extreme example is shunt resistance. It's very hard to get shunt resistance from a light JV curve, but it's very easy to get it from a dark JV curve. And there's other sort of parameters like mobility are a lot easier to get from transient photocurrent transients. So are things like, or at least guesses at the Urbach energy and sort of density of states and things like that. It's a lot easier to get from transients rather than steady state JV curves. So for this reason, some people often want to fit a model like gpvdm to multiple experimental data sets to try and narrow down their parameters they're trying to extract a lot more accurately. Now in this, what I do in this tutorial is I effectively work through fitting a light JV curve and then a transient photocurrent transient, so just two experimental data sets. Obviously you can extend this to as much as you to many parameters as you want, or many sets of experimental data as you want, but I just do this sort of dual example in this video. I'd say it's hard and it's quite an advanced thing. I don't expect most users to do this. So if you're sort of just using gpvdm to study the odd JV transient or whatever like that, then sort of skip this video. But if you are interested in doing sort of hardcore fitting, then do have a look at this video. You might get stuck because it's quite difficult, so just drop me an email if you do run into difficulties. So with that said, enjoy the video. So I've had a couple of requests recently to demonstrate fitting time domain data using gpvdm. Now this is quite a very complex process, and this is why I've not really made a video about this till now. So I'm going to go through this, and it's going to be effectively a matter of trial and error. So I'm going to sort of blunder through it in the way that I'd expect other people to blunder through it. And it's not going to be like my other tutorials are going to be sort of click, 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 just show you how to do it very quickly. This is going to be quite in depth. I'm going to discuss quite a lot about what's going on in the model. So you're going to need quite a bit of patience to go through this. So without further ado, let's continue. So I'm going to start off by making a new simulation, and I'm going to make an organic solar cell simulation. And I'm going to save it here. I'm going to call it test 1. Now, this is the standard solar cell simulation that sort of becomes the model. So if we look in the fit to experimental data, we've already got some data loaded in there. And we've got charge extraction in the light, charge extraction in the dark JV, light JV, and various other types of transient and steady state data. Now what I'm going to do to start with is just delete these, because I think we will learn more together if I do everything from the beginning. So if I delete this, delete the dark JV, I'm going to leave the light JV, delete all the others. Right, so we've now just got one JV curve, so let's just try and run a simple fit. And there we go. Now, the first thing to notice, or what I notice because I run these simulations a lot, is if we just run it one more time. Oops, let's run it here. So when it was running, it paused. It paused here at generating electrons and holes. There we go. So it was pausing quite a lot here. And this is because this particular simulation, this default simulation, uses a lot of trap states, and it's got to generate a file that effectively describes the relationship between electron densities in the traps and the Fermi levels. And the more trap states you have, the longer it takes to generate this file. So what I'm going to do is reduce the number of trap states just to try and make the simulation run a bit quicker. So we're going to go to electrical parameters, and then we're going to click on number of trap states, and we're going to set this to 5. So there we go. Then if we rerun this now, it'll just be a bit quicker. The other thing I noticed when running it is you can see up here, it says deleting directory, blah, 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 blah. We're trying to do a fit, and we're not really interested in how the electron hole profiles look within the device. So what I'm going to do is I'm going to turn off all this dumping. So this is just basically writing data out to show you how the different Fermi levels and things like that look. So I'm going to go to, and writing data disk takes a long time, and it's slow. We don't want to do this when we're fitting. The whole essence of fitting is trying to do it as quickly as possible, and then you'll get to an answer. So I'm going to go configure, configure, and then output files, and I've got turned on, well, dump optical information to disk, we don't need that. Dump verbose electrical solver results, we probably don't need that. So we're going to turn all those off, and then we're going to rerun it, and it runs a bit quicker, you can see. So that's good, it's running quickly. So it's worth just checking those things out before you start doing it with simulation. So what I'm going to do now is try and import the the TPC transients. So firstly, I'm going to clone this JV light curve. So I'm just going to clone that experiment. I'm going to call this TPC, just for a new name. Okay. Now, this is to all intents and purposes another JV curve being fit to the model, but I've just called it TPC. There's nothing about photocurrent in this simulation yet because we've not configured that. Interesting to note is that this button here, so you see this little tick here, that means we're fitting this data set, but if we turn that off and turn this into a cross, we won't be fitting this data set. So what this enables us to do is sort of fit one curve and then go back and sort of enable the fitting of another curve. So we can fit multiple data sets at the same time by sort of playing with this. So what else am I going to do? So let's import some experimental TCP data, so transient photocurrent data. So I'm going to click on the import experimental data button, and we're going to click open data file. Now in my desktop, I've already saved some experimental transient photocurrent data. So I'm going to open this up, and this data I think is at 1 sun and effectively 0 millivolts. So this here is open the data file up. Now this is the file to be read in, and this is the file that's imported into gpvdm. The game is gpvdm only accepts everything in SI units. It must be SI units. So we've got to effectively tell the software what this column is and what this column is. So I'm going to say this is time. I know this is time in seconds. And this one here is current, and I know this is in amps per meter squared. So if it was, for example, an amps or amps per centimeter squared or foot squared or whatever, it would convert this automatically for you into SI units. And now this is all SI units. So we basically import it now, and all of a sudden our JV curve's gone. We've got this very sharp step here and a very sort of long tail here. And there's a typical TPC transient when looked at on a linear scale. So we've got a very high peak here, and then it drops off very, very rapidly. So now I'm going to look at the configure fit window. Now, this is the start and the stop of where we're going to fit the data. So in the TPC curve, in the JV curve, we've got this value set as start as a millivolt and stop is 0.7 volts, which makes sense because we're starting at, if you look at the fit, we're starting about 0 volts and we got to 0.7 volts. The actual data in the JV curve goes from -1.5 all the way up to 1.5. So let's set something sane for the TPC. Well, I don't know. I haven't looked at let's look at the TPC data for a start. So let's go to test 1, and I'm just this is just my data. You can look at this in Origin or whatever you want. I'm just using GNU plot on Linux because it's easier for me. So let's have a look at this data just so we know what we're going for. So this is the data here. So we've got sort of a rapid rise here, and we've got this long tail here. So if we plot it on a log and then a log scale, so there's a log scale, this is what we should be expecting effectively. So when does it start? I don't know, my scale's a bit funny here. But I think it starts at, maybe I can turn this into nanoseconds. It's just GNU plot's a bit funny sometimes. So that's nanoseconds. There we go, nanoseconds. So I don't know, let's kick it off at 100 nanoseconds. Let's start the fit at 100 nanoseconds. So we're going to start the fit at 100 exp to minus 9. And when should we stop it? I don't know, 10,000 nanoseconds. So let's go, that's 1,000, 10,000 nanoseconds. So that should fit between there and there. Now, the other thing we've got is this thing called jv.dat. Now, that's not very helpful. So this basically tells us which file we're going to be fitting our simulation against. So if we go to the normal simulation window and we just click run, bump, like that, if we look in that simulation directory, so I'm just going to do this, actually no, we're going to do it here. If we look in that simulation directory, we have a file called jv.dat. Okay, so that's what it's fitting this against. Now, that makes sense for light JV curve, but not so much sense for the TPC data. So let's change that. So to figure out what file should we fit against, we're just going to flip the simulation mode into TPC, and we're going to click run, just like that. There we go. So we've done the TPC simulation. So here, all of a sudden, we've got a file called timej.dat. Now, notice it looks like the TPC simulation. Here's TPC. It looks like TPC simulation, except it's the other way around. And that's because, obviously, photocurrent's negative, and the person who measured this just flipped it around to make it look nicer. And if, in fact, we invert the axis and I think apply, can we apply log scale? Maybe not, maybe. Yes, it starts looking a bit like this curve here. So let's set that back now. So that was time_j.dat. So that's what we're going to put in here, time_j.dat. Okay, so that's looking hopeful. Now, we need to somehow tell, so I'll explain how the fitting process works. If we go, so this is the main simulation directory. This is home rod desktop test 1. What gpvdm does is for each one of these, so if we move this out here, each one of these tabs, so light JV, TPC, or whatever fitting you do, for each one of those tabs, it makes a new directory in the sim directory. And in there, it makes a new directory. So here we've just got light JV. And then to this light JV directory, it applies a new configuration. So I'll explain that process again. Basically, it takes this original simulation directory, and for each one of these tabs here, it makes a new directory in here and copies the simulation directory into that. Then it applies something called fit patch to this directory. So whatever configuration files in that directory, it's going to then edit to effectively make it a TCP simulation. So for example, if this was a standard simulation of your device and you wanted to fit a light and a dark curve, what it would do is it would copy the simulation directory twice into the sim directory, one for dark, one for light, and it would apply whatever fit patch was here to make the simulation light or dark. So, for example, if we wanted this to be a dark simulation, we would just write here light.imp psum, which is the power of the sun, and we'd just set this to 0.0. And now effectively it would be running a dark simulation. We don't want that. What we want to do somehow is change the mode of the simulation. So if you look at the simulation type, you can select, generally speaking, the mode of which simulation you want to do. So if we want to do a JV curve, we'll just click on JV curve and click run. If we want to do a TPV, we just click on TPV and click run. At the moment we're interested in this one here. So somehow I've got to tell the fitting parameter editor to do this sort of mode selection for us. Now, the way we do this is with the sim mode option. So the sim mode is stored in a file called sim.imp. Now I'm just going to show you this file. I'm going to take a bit of a diversion. First, where's it gone? If we look in the sim.gpvdm file, so this is the simulation directory. If we look in this file called sim.gpvdm, this is the standard sort of the save file of gpvdm. If we rename this to be a zip file, whoops, we can see actually there's a lot of files in this, and it's actually just the .gpvdm file is just a zip file. Now, if we look in sim.imp, so if we see here we had sim.imp. If we look in sim.imp, it's got sim mode, and here it's set to JV at JV. So here we've got sim mode, and then it's setting it to JV.jv. So this means we're effectively configuring a JV curve simulation. Well, we don't want that. So what we can do is let's put this file back to a gpvdm file, and let's simply click, let's select a TPC simulation there. Okay, now let's rename this file, oops, zip, and look in sim.imp, and it's written in here, simply because we've clicked on this thing, it's written in here, TPC 50 millivolts, one sun at pulse. This part tells it gpvdm which simulation mode to run, so whether it's a sun's VOC or whatever, and this is the specific type of simulation to run. So we're going to take that and copy and paste it into here. Now what this means is this will now effectively set the mode of simulation to be that. Right, so let's just rename that file back. Now, I realise it's a bit complicated and that's not super user-friendly, but this is part of the reason I've not made a video on this yet, because it's a bit complex and a bit in-depth. But hopefully, if you sort of struggle through this, then shoot me questions. We'll also be able to do it together. Now, whilst I'm on this topic of all those files in the gpvdm directory, I'll just bring this topic up that that I brought up in a previous video. There's actually something called a script editor, and in this script editor there's something called a hashtag dictionary, and what this enables you to do is effectively explore all those configuration files in the gpvdm file. So if we look at sim.imp, it basically tells us what the value is. So here it's actually set to TPC 50 millivolts, one sun at pulse. And that's quite a nice way to look at it. So if we change the simulation type to, I don't know, impedance spectroscopy, then look at it again. There it is. It's set it to IS at IS. So that's quite a useful little trick there. Okay, so back to fitting. Are we ready to fit? That's the question. We've set this up in the same way. We've set this up to be sane, so it's selecting the right simulation mode. I think we're ready to fit, so let's give it a go. There we go, what have we got? Oh, okay, so that looks a bit crazy. We've got our simulation's going negative, our experiment's going positive. This is looking a bit weird. So what's happening? Well, if you remember when I showed you the data previously, so I'll just get that up. I guess I'll just get that up. When you remember I showed you this, I told you that basically the person who measured this flipped the scale because obviously photocurrent is negative because it's leaving the device. So let's flip our simulated Y data, so invert simulated Y. So let's just do that and rerun it. Okay, so that looks more positive. We've got basically the experimental data and the simulated data going the right way. Now, I always do fitting of these on log scale because they're pretty log type things. So let's set the log scale, the Y log scale to be, let's do the fitting on the log Y scale. Now the important thing about doing fitting on the right log or linear scale is it sort of brings out the important features of the measurement. So I know, for example, that this drops off exponentially as a function of time. So it probably suggests you want to be fitting it on a log scale. Now, if you notice here, I actually did this, I set this to a log scale because I know the data looks a lot more interesting on a log scale, on a log time axis. For TPV it doesn't, but we can fit also on a log x axis by just flicking this on here. So if we rerun that, you see that starts to look quite interesting. Okay, now then, until now what we've been doing is we've just been running one iteration of the fit. We've not actually been letting it edit any parameters. We've just literally said just like run one iteration to let's basically see how it goes. So what we can do now is we want to run it. Now before we run it, we want to just check that everything we're telling it to do is sane. So, and in terms of fit, that everything's sane. So I'm just going to do this now. We're going to look at the configure window, and we're going to ignore this, and we're going to look at the duplicate window. Now the duplicate window basically copies material parameters. So for example, what this will do is it will copy so we've got this file called DOS0. This contains density of states, or the electrical parameters of the material. And we can edit this in a sort of a human-friendly way by clicking on electrical parameters. So this window here, this electrical parameters window, is basically the DOS0 file, which we're talking about here. So it says DOS0.imp. Mu FE is the mobility of the electrons, and mu FH is the mobility of the holes. So what this line would do is it would set the electron, it would effectively copy the electron mobility to the hole mobility. So it's basically symmetric simulation. So we're going to turn that on because I basically want to limit the number of parameters we're having to play with. Now, you might ask, well, how does I get this? How do I know this is the DOS0 file? How do I know this is mu E? Well, again, going back to, you can either use this sort of tool here to select which parameter you want to edit, or going back to the script editor and the hashtag dictionary, we can search for DOS0.imp, and then this basically brings up the contents of that file, and you'll notice that it's effectively the same as this electrical window. So there we've got, I don't know, so this is the tag in the file, this is the description. So here it says electron trap density, so we've got electron trap density 3.8 to 26, 3.8 to 26, okay? So it's basically just a representation of that file. Okay, so we've now effectively got with symmetric electron hole parameters, which I want to speed up the fit. You could decouple these, but I'm not, because I want it to be fit quite quickly. And then the fit variable window, what do we want to be fitting? Well, we want to be fitting the mobility. You can play with what you're fitting here. We want to be fitting the contact resistance, the shunt resistance. Free recombination, no, we don't want to be fitting that because I think it's 0 in the simulation. Yep, it's 0. What else? We could try fitting some of these recombination parameters. I'm going to see if we can get away with that, just because I'm hoping we don't have to. So now let's. In fact, what I'm going to do firstly is I'm going to only fit one thing at once. So let's turn off the TPC fit just for a start, and let's just see how it gets on with the JV fit. Let's just see if it can improve this error. Now I know, because I've done it before, it's going to struggle a lot, and I know that for this device I'm going to stop it there. Actually, the what we need to do is we need to slightly change the charge densities on the contact. So I've had a little play with this before, and if we go to the electrical parameter window, this is actually very high, so this is 1.2 28 to 27. That should be about 25, and this should be 5. And this is the effective density of states. And then on the contacts, so effectively we've got a very low VOC here because we've got very low charge densities on the contacts. When we look at the contacts, this was quite a low value. So I'm going to set this to 1 to the 25 and 1 to the 25 there. And I know that that should actually improve it because I've played with it earlier. Oh, or not, as the case may be. Let's go back to this. Let's have another look. 25 contacts. That looks reasonable. Should we give it? What else? Let's have a look at the density. See, I said we'd probably struggle. Look. So what it's done is it's randomly set the mobility to 0. Sometimes it does this. Sometimes it will just zero out a parameter for some unknown reason. So we put this at the 5, and it sort of there's a reason for it, but mathematical reason. But just watch out for it zeroing parameters out. Okay, run it again, and that looks a lot better. So we're now going to try and run the fit properly and see what happens. Now, I did say this is a bit of a complex process, and I'm going to sort of guide you through most of it, but it'll require quite a bit of messing around to sort of try and get it to work, generally speaking. So just have patience, and if you really get stuck, you know, you can shoot me an email and see how you get on. Yeah, okay, so still struggling a bit. We really want these JV curves to be a bit better fit. I might stop it now and just have a look at what it's done to the parameters and just see if we can help it along. Right, so I don't think it's been changing this electron trap density, which obviously will affect the recombination quite a lot. So I think I'm going to let it change that. I mean, I might even help it along. It's quite legitimate to help simulate the fit along by guessing. So that's very high, so I'm going to reduce it a bit and run it again. You see, that's a bit better fit there. This area here of the curve is probably due to shunt resistance, and maybe we could just reduce the shunt resistance. See how we get on there. Oh, and these minuses that appear here, it doesn't matter. It's sort of a mathematical artifact. That doesn't actually mean it's a minus. We could try and reduce that to 1, maybe. Little series resistance. Yes, series resistance. That's quite high, so I'm going to set that down to, I don't know, 5, maybe. Give it another bit of a run. Oh, no, that wasn't the fit. Run it again. Yeah, I mean that's not a bad. That's not a bad fit. Should we try and run it again, maybe? Or what we could actually do is we could try and maybe add in. So here I said that we don't really know this trap density. We could try and add in fitting the trap density. So if we go back to configure and look at the fit variable window, are we changing the trap density? End trap. No, we're not. Let's turn on the fitting of the trap density, electron trap density, and if we look in here, we're actually copying the electron trap density, the whole trap density. So now maybe we should be able to fit that a bit. So let's run that. Let's give it a minute. And the longer you leave it doesn't necessarily mean the better it'll fit. It might just be getting itself lost. So the key thing is sort of have a play with it as it's fitting. I think recombination is actually slightly too high because it's got a much bigger VOC. So let's try and fit or reduce recombination somehow. Or maybe just leave it. Or maybe change the charge density. We've tried to reduce charge. I'm reluctant to also start fitting the contact density because I don't want this video to go on for super long, but I might just try and drop it down very slightly and see if that helps the situation. I mean, we could be fitting these as well, but I don't want this video to go on forever, so maybe just run it again. This will be due to recombination not being quite right. Oh yeah, okay, we're getting there. So it's complaining about something here. Let's have a look. I saw an error message. There we go. Right, so it says, so what this is basically saying is there's some constraints that the model applies to the software whilst it's fitting. And it's basically saying file dos0.imp, number of electron traps, the value is 6.6 times 10 to 21, minimum value that's allowed is that one, the maximum value that's allowed that one, and therefore we're adding this error to the fit. So somehow the maximum value has only been set to be this. So we're going to allow this, which is actually quite a small value, 1 to the 20 per meter cubed. So we're going to set that to be a bit smaller. And we can do this with this one here. So didn't see that, we're just going to set this up to 25. And there should be an NH somewhere. NE. Well, that will fix that one anyway. Let's run that again. Now it doesn't complain. Okay. Yeah, okay, so this is looking much better now. Yep. There we go. Right. Now I'm going to stop the simulation before it actually converges properly. I'll just go back over that little thing that I did then. So these are basically the things it's fitting. So it's fitting, you know, the electron mobility, hole mobility, all these things. And then here are the maximum allowable and minimum allowable values. So for example, let's look, the contact resistance can go between 1 ohm and 200 ohms, which is sort of a sensible number. Electron mobility can go between -10 and -1 to the -4, which is a sensible number. And as soon as it goes out of those bounds, then it basically, the simulation adds a factor of 100 to the error, which is a huge amount of error. And it's just, the idea is to try and sort of encourage the algorithm to stay within these bounds here. And what we've done is this value here is strayed way out of, or this value here was to the 20, which was wrong, and the value we'd had in the simulation was way above 1 to the 20. So it was effectively adding a huge amount of error to simulation every time, and it just was sort of getting very confused by that. So that's what was happening. So we've now fit the JV curve in a sort of acceptable way. So what we're now going to do is turn back on the TPC simulation. So so it says don't fit this data. So we're going to fit this data and just run one iteration of this. There we go. So this is the, I'm just going to get rid of that error message. Right, so this is its attempt to fit the TPC curve, and this is its attempt to fit the JV curve. It's not actually yet fit the TPC curve, so this is actually quite impressive, I find. I mean, it's sort of a, you know, sort of prediction of the TPC curve just from a JV fit, which really shouldn't work, but it seems to have done it. Now, yeah, so now we've enabled this to be part of the fit by doing this. We're now going to just run it. And if you notice, both this curve and this curve aren't very far away from being converged. Like they're not bad approximations to what the experiment was. So if we now try and run this, it's going to slowly try and move all these curves at the same time. You see, but sometimes it'll improve this one and make this one worse. Sometimes it'll sometimes it'll sort of make this one worse and improve this one, but the overall effect will be that both curves will get a little bit better. So if we now go back to fit progress, we can effectively see, so this is the fit progress, this is the error function. I should really put some units on this graph. This is the error function as a function of fit. So this is, does it think it's done it? It stopped. I'm going to stop this and run it again. I think I've had this before. I'm not sure why. It's sort of a bit confused about what's going on. I'm just going to restart the software. I'm not entirely sure why this is. I think because we're messing around with it so much, I sort of got a bit confused. Right, let's go back to the fit window. Yeah, so let's run this fit again. See how it's doing. Okay, so didn't like that one. Might recover on its own. Indeed. You see it's trying to fit that one quite well. The fit progress is going down, so you can see this is how the fit error goes over time. So slowly the error is basically decreasing, and the error that you've got is effectively the sum of this green line here, so the difference between the simulation and experiment. Now I'm not going to bother, I don't think it's finished. I'm not going to bother continuing to fit this basically. I'll just show you one last feature which is quite useful. You can effectively change how much error each of these fits gives the total error. So it's obviously trying to minimize the total simulation error. So it's trying to effectively drive this total, the sum of the green lines to 0. Now, sometimes you might want to fit the JV curve super accurately and fit the TPC curve less accurately. And what seems to be happening here is the TPC curve seems to be being fit very well, and the JV curve less so well. What you could do is you say, well, actually, I want the contribution of the green line from the JV curve fit to be a bit bigger towards the error than the TPCs. And what this will do is bias to fit slightly more towards the JV curve than the TPC. So if you change this fit multiplier to say 2, and then rerun it, it'll boost effectively, multiply this line by 2, and the contribution of the JV curve will be lower than that of the TPC curve. So I think that's it really. This is quite a hard thing to do. This is not really this is not really something I expect the average user to do. This is sort of quite advanced stuff. So if you want help with it, then sort of drop me an email and I'll be happy to assist you. So that's it really. Thanks very much for your time, I guess.